All right, I'm going to take up your action potential homework and review the graph now, okay? So I haven't gone over the graph much with you. I know the video, Khan Academy video did that. It's time that we take a look at this graph, okay? And so a few important things to be seen. I've got so many different graphs. I've got a really good one up on the LMS page. I've got this one. I have a little one here as well. They all have something a little bit different to offer. So let's have a look at this, okay? Actually, I think the one I'm looking at, the one on my screen right now in LMS, that's probably the best one I've seen in years. So we have the resting potential of minus 70, okay? As we go along this graph, you can see that what's happening is the neuron is becoming more and more positive. So this is usually referred to the minus 55 or the minus 50 when the sodium channels close, when the sodium channels open. This is usually referred to as the threshold of excitation, okay? And so minus 55 is a really important number, okay? And some diagrams will have it as minus 50. You can't get too caught up in that exact number. So I just said minus 55 is an important number. It's an important number on this diagram. Sometimes you'll see it as minus 50, okay? Different neurons, different thresholds. But what we're seeing here is we're getting a little change in the membrane potential. So we're going from minus 70 to minus 55. And at this point here, for this neuron, this is when we decide that the stimulus is very important and we're going to go forward with the action potential. Okay, so we have a number of minus 55 on my note. I said minus 55 or minus 50. I can't remember what number I gave you there, or if I did even give you a number. And at this point, we're going to go forward. Okay, so on this side here, this is called depolarization. So we're going to depolarize the membrane. In other words, it was polarized definitely at minus 70 millivolts. And now we're going to head up and we're going to depolarize. See, we're going to 0, okay? And then we're going all the way up to positive 30, positive 40, somewhere in that area. All right, again, different graphs, different numbers because we have different types of neurons. At this point here, this is called the peak action potential. So one thing I do want to note, once we get past this, it's all or nothing. So once our neurons decide, they're going to send a message. Once they get up into this area, they are going forward. Okay, so it's kind of like being on a roller coaster. Maybe you can still signal somebody to get off down here, but once you're going up that hill, you're on your own and you're going down. You know what's happening. So at this point, the action potential is going forward. We are fully depolarizing. We're going from 0 to positive 30, and this is called the peak action potential. Okay, so you can see it's the peak, right? At this point here in that peak action potential, this is when you're going to get your sodium channels closing. So sodium closes and potassium opens. Okay, and our sodium potassium pump is going to kick on too. NAK pump, which works all the time to maintain your membrane potential. So I'm going to say that one more time. Your sodium potassium pump is working almost constantly to maintain this number. Okay, remember it's negative because 3 positives are taken out, 2 positives are brought in, and so we maintain a negative potential. And that's because this guy works tirelessly to do that. Of course, when this is happening, it's going to work even more. And a long time ago, I heard that this uses more ATP than anything else. I'm not sure if that's completely accurate, but I do want you to be aware it uses lots and lots of ATP to do this, okay? To maintain this number. Why? Because our nerves are extremely important in interpreting the information in our environment. All right, so that happens. And then we go down this ride of the roller coaster, okay, where sodium ions are exiting. Okay, so those channels, the sodium channels are open and we're going to repolarize. So that's the whole goal. We want to repolarize here. What happens is the sodium channels stay open a little longer than they need to, and that's called hyperpolarization. Okay, so in other words, we go down lower than minus 70. Okay, minus 80, minus 90 sometimes. That's hyperpolarization. And then we go into our resting state, which is in this area. Okay, when this is happening, okay, oh, you actually have all this over here. So you can actually see what's happening here. So we've got all of this. This diagram labels everything. Okay. Why did I put equilibrium there? Just because the sodium, or sorry, the Khan Academy video explained something to me that I caught on to, where it says that this is the equilibrium for sodium inside the cell and outside of the cell. So in other words, when you've got an equal amount of sodium inside of the neuron and outside of the neuron, right now we believe that that potential is at positive 30. Okay. So when not so much positive 30, sorry, it's when you have the peak action potential. At that point, you've reached equilibrium of sodium inside and outside. Okay, it's just an interesting fact that I picked up on this semester. Okay, you're always learning, right? I'm always learning too. So I think I've gone over this with you. In hyperpolarization, we then go into a refractory period. So we've got a refractory period right here, and the refractory period is extremely important, because it means that the neuron cannot fire. So there is no firing. There is no action potential. Whoops, firing. You're going to have to pretend that word is firing. Okay? So no firing allowed during that refractory period. And that is to prevent the communication from going backwards. So I said to you, the neuron sends a message in this direction. If this particular part of the membrane can no longer fire, that means it's resting. That means only the parts of the neuron to come can be firing, okay? And that, again, make sure that if the message is sent from the senses to the brain, that the message doesn't go back to the senses, okay? That would be a waste of all our energy. So common theme in this whole course, right? Let's not waste energy. So we keep the refractory period, we keep the action potential going in this direction, because at this point, the neuron is resting and it cannot fire. Okay, for a fraction of a second, it can't fire. I know fraction of a second isn't long, but for the neuron, that's awesome. Okay. So you have my notes in that package. If you want them, they're here to be read. All right. You've got all of that stuff. Sometimes I teach with this diagram, but this time we drew it out. So you've got all that extra information. It's there for you. And then I had you do these questions here. So why does neural signaling proceed in only one direction? And that's because we have a refractory period. And if you answered that differently and you thought, well, why does it do that? It's certainly to save energy and to be much more efficient. Explain the movement of ions in a neuron that has each membrane potential. Okay, so if we look at, and you have many diagrams to look at, if we look at minus 70 millivolts, so explain the movement of ions. So at minus 70 millivolts, you're going to have a few leaky sodium channels and potassium channels, but basically things are staying put and the sodium-potassium channel is working, or sodium-potassium pump. At minus 51, okay, so I'm going to get this one here that I was working with you guys. At minus 51, if we look at this diagram here, what's happening is that we've got some sodium coming into the cell. Okay, those leaky channels are allowing some sodium to come into the cell and say, wake up. Okay, and on the diagram that I have for you on the LMS, it actually shows you in here failed initiations. Okay, so in other words, sometimes we decide it's not that important, and then so the information is never sent forward up here. Okay, so in that area, you've got the sodium leaking in, but it hasn't passed the threshold yet. And so that means the signal is not going to get sent to the next to the next neuron. Potentially not sent. At minus 51, it could still be going up there. We were not sure on that question. So minus 49, they're picking a number that's beyond minus 50 to be safe. At minus 49, we're going to be in this area. And so in this area, voltage-gated sodium channels are open and leaky sodium channels are open, and we are going forward with the action potential. So sodium channels are open. At 0, same thing, okay? Sodium channels are open. At positive 30, sodium channels close, potassium channels open, the NAK pump kicks on, all right? And then lastly, in multiple sclerosis, myelin is progressively lost from axons and replaced by hardened scar tissue. Given what you have learned about the function of myelin, explain how the degradation of myelin might affect the transmission of nerve impulses. So, if you have, I'm going to draw on this note, you have your axon, okay? And we've got it myelinated, all right? So this is myelin, myelin, Okay, and you have this from the first note that I gave you. So even though myelin is white, I'm going to put it in yellow. Okay, so remember, on a person with a healthy amount of myelin, what's going to happen is nervous transmission, the action potential, is going to jump and it's going to go faster. So we're going to get membrane potential changing there, membrane potential changing here, membrane potential changing here. So you can see we don't have to go all the way along, okay? We're going to have saltatory conduction. When this starts to break down, okay, that means that our nervous transmission is going to be going, I'm showing no myelin, okay? If there was no myelin, nervous transmission would be going along like this. So you have to figure, this has a sodium-potassium pump, this has sodium-potassium pumps. We're looking into the action potential in every one of these places. This saves sodium-potassium pumps from turning on all over the place, which uses lots of energy. So that's number one. People without myelin or breaking down myelin are going to have a lot less energy because their nervous transmission is going pretty much along the length of the axon. I mean, there's scar tissue, so you can say, okay, maybe it's going to jump like this a little bit, right? And I'm really making it a severe case here, but you can see what I'm saying. You're going to have the action potential riding all the way along here. So number one, it's slower, okay? Number two, it requires a heck of a lot more energy because you are firing all along the length of this axon. All right, I hope that helps you.